Afternoon. So Dr. Nietzsche is away today, so I'll be running the lecture. Now, last time you guys saw me up in front here, we were talking about light as a particle and light as a wave. So we've kind of come a little ways since then, and we started to move to describing chemical bonding and how we have bonds moving from atoms on our periodic table to molecules that we can do chemistry with. And since this is chemistry class, bonding is fairly important. So we start with the impetus for having these chemical bonds form is we want to get to a stable electron configuration around every atom. So if we look at our periodic table, we first need to consider the valence electrons. So valence electrons are the outermost electrons on an atom, and that is where we get bonding. So for example, hydrogen has one valence electron, helium has two valence electrons, and then we go down to lithium. While lithium has 3 total electrons, only the 2s electron in lithium is in the valence shell. The others are the valence orbital. The others are in the 1s orbital, which are the core electrons. So it's these outermost electrons which are the ones that participate in bonding. And this makes sense because if we're bringing two things together to form a bond, the first interaction we're going to have is those outermost electrons. Okay, if we push the nuclei too close together so the core electrons are interacting, then we get into nuclear repulsion and things like that. So we look, and our stable configuration we get from looking at the noble gases. So these are our helium, neon, argon, krypton, xenon, radon, and they have full sets of orbitals. So for example, helium has 2, neon has 10, which in the valence shell is our 2s and our 6 2p electrons. And that's where we get the 8 that comes in the octet. So when we have these compounds forming bonds, we want to share some of these electrons around so everything can have an octet or a set of 8. So this Lewis theory, we share these electrons. Now the first one we talked about is ionic bonding. And ionic bonding is when we completely transfer an electron from one atom to a different atom. So for example, if I have lithium fluoride, if I look at lithium and I want to get to a noble gas configuration, I can either gain 7 electrons to get to neon, or I can lose 1 electron to get to helium. So of course, the path of least resistance is to lose that 1 electron. And we know from talking about electron affinity that we can't pile 7 electrons onto a lithium because there would be far too much repulsion for that nuclear charge. So that is not possible to happen. So lithium just wants to lose this 1 electron. Now on the other side of things, if we look at fluorine, right? Fluorine has 7 valence electrons, and so it only needs to gain 1 electron to get to its full set octet of 8 electrons, as opposed to trying to take off 7 electrons from fluorine, which we know from successive ionization energy is it's harder and harder to take off the electrons the more and more we take off. So we have lithium that would prefer to just give up 1 electron, and fluorine that would prefer to just gain 1 electron. And isn't it great when things just work out? They say lithium will give its electron to fluorine. Fluorine will gladly accept that electron. They both now have a noble gas configuration. And then we have the positively charged lithium next to the negatively charged fluorine. And we know from Coulomb's law that if we have a plus and a minus sitting right next to each other, they're going to stick together. And they're going to stick together pretty strongly. And so that's how we get to ionic bonding. Now, we also had said that ionic bonding happens when we have a large electronegativity difference, right? And this gets back to, again, our periodic trends, because we know that fluorine has a very high electronegativity and lithium has a very low electronegativity. Fluorine likes to take on electrons. Lithium is better at giving off electrons. And so it just all comes together to give us this ionic bond. We can do the same thing for sodium chloride. Again, sodium's valence electron is this 3s1 electron. So it can lose one, and then it gets to a neon electron configuration. Our chlorine, it has 3p5, so gaining one electron gets it to 3p6 or the argon configuration. And so again, we transfer this electron completely and then rely on our Coulomb force to hold this together. Now this also works for things like magnesium. Over here, something like magnesium or calcium, they can lose 2 electrons to get to the noble gas configuration, and that will give them a +2 charge. And if we have a chlorine there, we need to have 2 chlorines because every chlorine only wants to take on 1 electron. So we can have this. Now these are the alkali and the alkali earth metals over here. So that's great. Ionic bonding works pretty well because everybody's sort of happy there. Everyone has an octet. We've got a stable charge. But what if we're talking about things over in this part of the periodic table here? Like we're talking about nitrogen, oxygen, sulfur, fluorine, chlorine. All of these, their closest route to get to that noble gas configuration is gaining electrons. And since they both want to gain electrons, we can't completely remove them from either one. So what do we have to do? We got to share. We've got to go back to our kindergarten rules, and we got to share our electrons so everyone's happy. And that's what covalent bonding is. It's the sharing of electrons between 2 atoms to form a molecule. So what we have here is a depiction of a bond forming in something like H2. So where we have these 2 hydrogen atoms, each with 1 electron, and much like we can think about, we talked about the de Broglie wave relation, right? We can treat an electron as a wave, and so we can describe that with this wave function. And 2 of these can constructively interfere to form a bonding interaction. So constructive interference from these gives us a bonding interaction. So what we have here is C, hydrogen. Hydrogen has 1 electron, and this hydrogen has 1 electron. If they share one with each other, there's 2 in between them. So that forms the bond. There's 2 around this hydrogen and 2 around this hydrogen. So hydrogen has the duet rule because, again, helium is the first noble gas, and it only needs 2 electrons. We also can look at chlorine here. Chlorine has 7. And chlorine can share 1 electron with another chlorine. And if we share back and forth here, we form a bond. We have our octet around this chlorine and our octet around this chlorine. Now, these 2 cases here, H2 and Cl2, are called homonuclear diatomics. That means diatomic 2 atoms and homonuclear of the same nucleus, or the same atom, right? Both Cl's are the same. So what do you think about the polarity in this bond? It's neutral because they're both the same, and they both have the same electronegativity, so there's no electronegativity difference across this bond. So that's the form of a perfectly covalent bond. It's shared very equally between our 2 atoms because they both have the same electronegativity. Now we can move to something like HCl here. HCl, we have our hydrogen with its 1 electron. We have chlorine with 7. So we have 8 total electrons. We can form a bond, share electrons between HCl. We make this bond. Hydrogen has its duet. Chlorine has its octet. But in this case, we have 2 dissimilar atoms, which are going to have different electronegativity values. And our electronegativity represents how bonds are shared, how electrons are pushed around when they're shared in a bond. And so chlorine has a higher electronegativity than hydrogen, so it's going to sort of pull the electrons towards itself a little bit. So that's ionic bonding and covalent bonding. So we use this to get into our Lewis dot structures, which are a model to represent chemical bonding and predict structures, bond strengths, bond lengths. Also, next week, we'll get into describing molecular shape from our Lewis dot structures. And so what Lewis said is, he noticed that these noble gas configurations are really stable, and so we kind of want to get to that if we're a non-noble gas. You want to be like that noble gas. So we've seen various things like CH4 here, carbon, which has 4 valence electrons. Hydrogen has 1 each, so we have a total of 8 here, and so we'll form 4 bonds. Carbon has 4. It needs to get 4 to get to the octet, so it shares with the hydrogen, forming 4 bonds. We also have NH3 here, again, nitrogen with 5, 3 hydrogens, we have 8 electrons again. But we only form 3 bonds to make this octet around nitrogen because it's got this lone pair, because it has more electrons than carbon. It doesn't need to share as many to get to its octet. Now here we have a couple more of these homonuclear diatomics. We have O2, oxygen with 6 valence electrons, so we've got 12 total electrons for O2. Now, we have to make a double bond here because if we wanted to have a lone pair if we wanted to have an octet around each oxygen with only a single bond, we don't have enough electrons to do that. We would need 14 electrons. Like chlorine, Cl2 has 14, so we only have to share 1 each way. Oxygen needs to share 2 electrons to get to its octet because it only has 6 valence electrons. Likewise, if we move to N2, N2 is only going to have 10 total electrons. And so it's got to share 3 each way to form this bond. So we can see moving from Cl to oxygen to nitrogen, they have the same arrangement, right? They're just 2 atoms forming a bond. But as we decrease the number of electrons, we have to increase the number of bonds or increase the sharing in order to give everyone an octet. Whoops. Now, if we move to something like carbon monoxide has 10 electrons, 4 from carbon and 6 from oxygen, which is the same number of electrons that we had in the case for N2. So these two are referred to as being isoelectronic because they have the same atomic positions of the atoms and the same number of electrons. So since they're isoelectronic, we see that we have a triple bond here for CO. You see how the electron configuration for these two is the same. Our Lewis structure is the same because they're isoelectronic with the same number of atoms in the same position. But what's the big difference between these two? Yes, polarity. Now we have dissimilar electronegativity, so this bond is going to become polar. Now, Lewis theory isn't perfect, and it doesn't describe, every chemical compound that exists in the world. There are some exceptions to this rule, but it's a good approximation, especially for the S and P blocks. Once you get into the D electrons, Lewis theory does not predict theirs as well. So there are limitations, but for a lot of simple compounds, Lewis theory works rather well. Some of the exceptions, though, like we had BF3. Boron only has 3 valence electrons. Fluorine brings 7 to the table, so we've got a total of 24. Now, this would give us, if we give an octet around all our fluorines, in order to get the octet around boron, we would have to form a double bond between a fluorine and a boron. And since fluorine is the most electronegative, it doesn't like to share electrons. So instead of forming that double bond, we're just left with an electron-deficient boron in the center. So if we had NH3 and BF3, we can actually react these two because there's a lone pair, a free lone pair around this nitrogen, and this electron-poor boron really would like another set of electrons, and so these can react to form a bond. We also have xenon tetrafluoride. Now, for quite some time after Lewis theory came around, there were several people who didn't think that noble gases would form bonds because they already have an octet, so what's their reason to share if they've got all the electrons they could ever want? Well, as it turns out, if you put a pretty extreme reaction conditions with fluorine, you can actually trick xenon into making bonds, which it really doesn't need to do. It's already got an octet. But if we use something like fluorine, fluorine is really electronegative. It really likes grabbing onto electrons. And if we look at xenon here, xenon's got a pretty big atomic radius. It's got a lot of electrons. So if the conditions are right, fluorine can come in and get some of those away, and we can form xenon-fluorine bonds. Now we're left with, however, how many electrons do I have around my xenon? 12. So it has more than an octet, but this is called expanding to the octet, and it's another case on this Lewis theory. So having talked about all that, let's do a chem quiz. What's the correct Lewis electron dot structure for formaldehyde? Formaldehyde was often used to preserve as a preservative, and it's a rather nasty smelling compound. So CH2O, what is the electron dot structure for formaldehyde? 1.5 minutes. Let's see how many people we got. What did we have last time I was here? 2:30? 2:30? It's Friday though this time. I don't know. I bet we can get 2:20. Let's see. Don't forget to click in. Make sure we all vote so we can get our iClicker credit. Lewis dot structure for formaldehyde. What is the best one? A, B, or C? $190. 30 more to get to 220. 43 seconds. $20 seconds. Don't forget to vote. 230. All right. Can we get 240? 236. 4 more people. 3, 2. Come on, give me 240. All right. There we go. A lot of people here today. 3 seconds. 241. All right. Let's see what we got. All right. I like the way this looks. Oh, our Joker's back. Oh, isn't that funny? There wasn't a D choice. Man, that person's hilarious. All right, so I think we're mostly on the same page here. So let's move on. And if we look at CH2O, first thing we need to do is count up our electrons, so we know how many we have to form the bonds here. Carbon brings us 4. Oxygen brings us 6 valence electrons, and 1 from hydrogen times 2 gives us 2. So we've got a total of 12 electrons. Well, let's look at B, right? We have 1, 2, 3, 4, 5, 6 pairs of electrons, which is 12 total. However, my carbon has 10 electrons around it. That's no bueno. Carbon doesn't roll that way. You can't make 5 bonds to carbon. So it doesn't have an octet. It has more than an octet. So that's not good. This guy has 1, 2, 3, 4, 5, 6, 7 pairs, 14 electrons, and we only have 12, so we've put too many electrons in, so that won't work. So A is the answer. We can see we have 1, 2, 3, 4, 5, 6, 12 electrons. We have a double bond between carbon and oxygen. Oxygen octet, carbon octet, hydrogen duet, hydrogen duet. There we go. That is our Lewis dot structure. Okay, so now we're going to move on to a new slide here. So now we're going to move into a little more description of bond order, resonance, formal charge, some more descriptors of working with this Lewis theory. So, again, to beat chemical bonding into the ground. Now, about chemical bonding, if I form a bond, do I release energy or do I need energy? Release. Can't stress that enough. By forming a bond, it becomes more stable. If bonds were higher energy than being not bonded, we would never form bonds. Right? It wouldn't be favorable to go higher in energy. So when a bond forms, energy is released. Very important. So I already talked about ionic bonding, where a more electronegative element captures the electron, like lithium fluoride. Again, we can get to a noble gas configuration this way. One's a plus, one a minus. Coulomb attraction is pretty strong. And covalent, which is sharing. If we're not giving and taking, then we must be sharing electrons, such as Cl2. And we can also get polar bonds like HCl. Now, this cloud here is a representative of the probability of finding an electron around HCl. Now, we remember from looking at our atomic orbitals, right? They were a description of the probability of finding an electron in a given orbital. So this is one for a molecule, and we can see that chlorine, which is more electronegative, is going to pull the electrons in that bond towards itself, which is why we have a delta minus here and a slightly larger electron cloud. Then there's a smaller probability around this hydrogen because it's less electronegative. If we were to have this for Cl2, it would be a perfect oval. It would be even around both because there's no electronegativity difference. Now, for the diatomic, the dipole of this molecule is the same as the bond dipole because there's only one bond. But as we move to 2, 3, 4 atoms in our bond, we have to work with the bond dipoles to figure out the molecular dipole. And usually if we've got symmetry, symmetry is going to tend to cancel out these bond dipoles. So here we would have a central atom with 2 equivalent atoms bonded to it, but they're in a linear fashion. So the polarity of that bond is going to be pulling in equal and opposite directions. So even though the individual bonds have a dipole, the net dipole for the molecule is going to be 0. Likewise here, the 3 case is a little bit trickier to see. So we've got a central atom with 3 equivalent things bonded to it. So we have 3 equivalent bond dipoles. Now, if we do the vector math here, the vertical components of these 2 vectors are going to cancel out, and we're left to sum their horizontal components, and they will sum to an equal and opposite magnitude of here, and that'll cancel out. So this symmetry is going to lead these bond dipoles to cancel and leave a molecule with no dipole. Now, if we don't have that symmetry, then we can get an overall dipole. So like this case here, this sort of V shape, this is like we would have in, say, water. H2O is V-shaped, and it has a dipole. Water is polar. We saw this on Wednesday with the burette and the charged rod, right? You can bend the stream of water, but you can't bend the stream of hexane. Right? Remember that with the fur and the rod? All right. So here what happens is we've got 2 bond dipoles, and while the horizontal components will cancel, the vertical components are now additive. So the molecular dipole will bisect this angle right here. And then finally, in this case, again, we've got 2 equivalent bond dipoles here and a stronger bond dipole in this direction. So now this horizontal component is bigger than the sum of these horizontal components, so we'll be left with a dipole on our molecule again. And in chemistry, we draw our dipoles, I believe, different than physicists. So the plus like this is the positive end, and the arrow is at the negative end. So that's how we usually draw our bond dipoles. The longer line means it's a stronger dipole, right? Because it's a longer dipole, it's a stronger dipole than the shorter ones. So since it's a vector, the length of the arrow indicates the strength. Okay. All right, another chem quiz. Let's see if we can do this. Remembering about our dipole symmetry here from our Lewis structures, which of the following molecules does not have a dipole moment? Does not have, does not, or does not. I guess we'll go with that. A, B, or C? See what we got here. So we got carbon monoxide, carbon dioxide, and formaldehyde. I think we've seen all of these before. 50 seconds. Don't forget to click in. All right, we got 10 more people. 241, that's the number. One more. There we go, 241. Any late arrivals? No? Dang. No late arrivals today. Although I haven't scared anybody off. This morning there were fewer people on the second chem quiz. Ah, 242, all right. We got a late arrival. Okay, and let's see what we get. Yes! I'm going to go ahead and agree with that. So, for completeness' sake, let's work through this. So we have carbon dioxide here. If we look, yes, the CO bonds have a dipole, but since this is linear, they're equal in opposite direction and they're going to cancel, much like this case right here. So that's our carbon dioxide. If we look at formaldehyde, we have this polar CO bond. Now, the magnitude of this dipole is much greater than the magnitude of these. Like, I don't really think of C8. There's a small dipole, the small electronegativity difference between carbon and hydrogen, but it's pretty negligible, especially compared to this CO dipole. So we'll have our overall net molecular dipole in this direction. And again, carbon monoxide, it's one bond, and that's all that's in our molecule because we only have two atoms. So the bond dipole is the molecular dipole in this case. And that gives us B. Carbon dioxide does not have the molecular dipole. Now, one of the things that dipoles are important for is that is how microwave ovens work. So when you're up at 3 a.m. on Monday morning trying to finish your homework set before it's due at 9, and you need some ramen to get through the night. I don't know if you guys still eat ramen noodles. When I was in college, that's what we used to eat. Still? All right, I'm not that old yet. Excellent. But how microwaves work is the microwave oven drives rotations if you have a molecular dipole. And the big thing that does in most of our foods is water. So what a microwave does is it drives rotations in the water, and these spinning waters generate friction, and that's what heats up our food. So things like fat, which doesn't have these dipoles, isn't going to be as affected by the microwave, whereas water is going to really strongly interact there. So that permanent molecular dipoles are important for rotations, and that's how microwave ovens work, in case you were wondering. Okay, let's move on to talking about resonance structures and bond order. So we'll start with ozone. I've got 3 oxygens. My oxygen has 6 valence electrons, so I'm going to have a total of 18 valence electrons in my compound here. Now, I have to form this double bond because if I were to have a lone pair here and a lone pair here to give the octet, I would need 20 electrons to do that, and I only have 18, so I'm forced to give 3 bonds to one of the oxygens. But which one I make a double bond and which one I make a single bond is fairly arbitrary, right? Could I have drawn it with the double bond here and the single bond there? I'm pretty sure I just did. So, you know, whichever side we do it, these are equivalent. Now, ozone doesn't know Lewis theory. Ozone doesn't know that it should have a double bond or a single bond, right? So what we actually observe is somewhere between these two cases. We see an average of our resonance structures is what gives us the accurate description. If we were to look at ozone with spectroscopy or something, we would see that it actually has equal oxygen-oxygen bond lengths. Okay, each one is the same, and it comes from sort of an average of these two resonance structures. So what does that mean? Well, we want to figure out what the bond order is. Now, what bond order is, it's a description of it's a measure of how strong a bond is. So a single bond has a bond order of 1, a double bond has a bond order of 2, and a triple bond has a bond order of 3. The system works. So we can talk about the case for our resonance structures, and they're going to have, in ozone, we're going to have a bond order of 1.5. How do we get there? Well, it's a double bond. This bond is a double bond here and a single bond here. So we have a bond order of 2 and a bond order of 1. So in the combined resonance structure, this bond has a total bond order of 3, but there's 2 resonance structures, so we divide the bond order of 3 by the 2 resonance structures, and that's how we get to 1.5 bond order, right? We average out the contribution equally of each of our resonance structures. So let's look at carbonate, CO3 2-. We make our Lewis structure here, count up our electrons, and we end up with 1 carbon-oxygen double bond and 2 carbon-oxygen single bonds. But the position that I place this double bond in, again, it doesn't matter which one is the double bond and which one is the single bond. So I have one for all 3 of those cases. So now I have 3 resonance structures contributing to what I observe in the molecule. So what's my bond order going to be? Well, if I look at the top CO bond here, I have single bond, bond order 1, bond order 1, bond order 2. Total bond order of 4. This is across 3 resonance structures, so 4/3 gives me a bond order of 1 1/3. And all of these CO bonds are going to have the same bond order of 1 1/3. We can also have the case of benzene. And if you move on to 3A and 3B, you will come to know benzene well. And what we have in benzene is we have a ring. These are carbons. We have 6 carbons in this hexagon. We have 3 double bonds and 3 single bonds. And they alternate double, single, double, single. But if I draw it, I can draw it this way, or I can draw it that way. And what I actually observe, again, is the average of my resonance structure. So the bond order in benzene is going to be what? I have a bond order, if I look at this bond here, I've got a double bond here and a single bond here. So my bond order will be 1.5, right? Bond order 2 plus bond order 1 divided by 2 resonance structures gives us a bond order of 1.5. Okay? All right, stick with me, my story gets better. Chem quiz. All right, so let's look at this here. Think about NO2 minus and NO3 minus. How does the NO bond order change when we move from NO2 minus to NO3 minus? Does that N order bond order increase, decrease, or stay the same? Let's see what we got here. Let's vote. NO2 minus and NO3 minus. We're starting at NO2 minus, ending at NO3 minus. Is my bond order going to increase, decrease, or stay the same? .230, we got 12 more to go. 11, 10, 9, 8, 7, 6, 5. 9 seconds. Don't forget to click in. All right. Wow. That's even more even than it was this morning. All right. Well, looks like we've got some discussions to do here. All right. Hold on a second. Now, so bond order is a description of the strength of the bond. So a double bond, bond order 2, single bond, bond order 1. If we have resonance structures, the bond order is going to be the average of that bond in the resonance structures. Now, also, remember when I said at the beginning when we were looking at carbon monoxide and N2, right, where I said they were isoelectronic? And they had the same Lewis dot structure. How many electrons does NO2 minus have? 18. And it's in this shape. What did we see with 18 that has that shape? What about NO3 minus? How many electrons do I have there? I would have 6 times 3, which is 18, plus 1, which is 19, plus 5 from nitrogen gets me to 24. Have I seen something with this skeleton that has 24 electrons that it could be isoelectronic with? Got to think about resonance structures. Got to think about the averaging of those structures to get me bond order. Let's try this once more time. Talk amongst yourselves. Let's discuss. Make noise. Convince your neighbor. See if we can get to a consensus here. Gotta get truck into formal charge. All right, we gotta go here. We gotta go. I got 8 minutes, so I gotta do formal charge. "24 seconds. Don't forget to vote in." Still got about 30 people left to go. Don't forget to click in, get your attendance credit. 8 seconds. All right, let's see if we got somewhere here. Decreases. We're moving around, so we're thinking C. All right. Let's take a look at this. Let's sort this out. Okay. So, if I have NO2 minus, right, it's isoelectronic with ozone, and it has the same skeleton form here, so it's going to have the same Lewis structure as ozone. What was my bond order in ozone? 1.5, because I've got 2 resonance structures, and I'm alternating between a double and a single bond. Double bond has bond order 2. Single bond has bond order 1. The total bond order in the 2 resonance structures for this is 3, 2 plus 1, divided by 2 resonance structures. Total gets me to 1.5. Now, what about NO3 minus? It's isoelectronic with CO3 2 minus. So they're going to have the same Lewis structure. Again, we see 1 nitrogen-oxygen double bond, 2 NO single bonds. There's 3 total positions, so like CO3, our bond order is 1 1/3. So that means the bond order decreases when we move from NO2 minus to NO3 minus. All right. 2 more slides, and then we can have some fun. So stick with me through formal charge. So what formal charge is a way of assigning a sort of charge state in a covalent electron distribution where we're sharing electrons. Now we see that this NO2 has an overall charge, right, of -1. And formal charges give us the charge of each individual atom, and the sum of the formal charges on the atoms must equal the overall molecular charge. So the way we start this is we share electrons equally. I look at nitrogen. It's got this lone pair, which it isn't sharing with anyone, so those 2 electrons belong to the nitrogen. We go to the bonding electrons, and we share them equally across the bond. So there's 4 bonding electrons here between nitrogen and oxygen, so 2 of them go to nitrogen. Here there's 2 bonding electrons between nitrogen and oxygen, so 1 goes to nitrogen, giving us a total of 5 electrons to nitrogen. If we look at this oxygen, it has 7 electrons, 6 lone pair electrons, and 1 bond, right? The bond gives us 1 electron because the bond is a pair of electrons, and we're splitting them evenly because it's a covalent bond. So this oxygen has 7. Now the way we get out of formal charge, how many valence electrons does neutral nitrogen have? 5. Nitrogen comes with 5 valence electrons normally. And I've got 5 assigned to it in NO2 minus, so my formal charge, for my formal charge on this one should be 0. On oxygen, it has 6 valence electrons, but in my Lewis structure, I've got 7 electrons around this oxygen, so I have 1 more electron on oxygen than I do valence electrons in a neutral oxygen, so its formal charge is going to be -1 because it's carrying an extra electron relative to its nuclear charge. So my formal charge, we compare the valence electrons it has versus now the valence electrons it's given. So this has an additional electron once it forms this compound, which is why it's -1. Now, as I said, my formal charges on each individual atom have to add up to the formal charge on my molecule. So the formal charge on this oxygen, which is different from this oxygen, right? The formal charge on this one had better be 0. And it is, because I've got 1, 2, 3, 4 lone pair electrons. I have 2 bonds giving me 1 electron from each for a total of 6 electrons around this oxygen, which is how many oxygen has in its neutral state. So its formal charge is 0. We have 0 plus 0 plus -1 gives us the -1 overall charge. Now, we can use this formal charge to predict what the best Lewis structure is. If we have OCN minus, there's 3 potential Lewis structures here. We could have a C triple bond O, double bonds on either side, or a C triple bond N. Now, the 3 rules for formal charge. 1, we want to minimize the formal charge on the individual atoms. We want as many of them to be 0 as possible. 2, we want the negative charge to be on the most electronegative atom. And that's because the most electronegative atom is the one that wants the electrons in the bond the most, so it's going to be the most stable, carrying that negative charge. And finally, we want small formal charges on our individual atoms. That's better than large ones. We would rather have, if we have to have a charge, we'd rather have plus or minus 1 than plus or minus 2. So if we look at these 3 cases, for here, we have nitrogen, 1, 2, 3, 4, 5, 6 lone pair electrons. 1 from this bond gives me a total of 7 electrons, compared to 5 valence electrons gives me a formal charge of -2. Carbon has 1, 2, 3, 4 bonds, which give 1 electron each, so it has 4 electrons in this Lewis structure. It has 4 valence electrons, so it gives us a formal charge of 0. And my oxygen has 2 lone pair electrons, 1, 2, 3 bonds, so 3 electrons from the bonds gives us 5 electrons to oxygen. We know it has 6 valence electrons, so that gives a formal charge of +1. So this one is pretty much 0 for 3 because I've got formal charges on two things, and I've got a 2, and my negative is on the not the most electronegative atom. Oxygen is the most electronegative, so that's where I want to put the minus charge. If I do equal C double bond O each side, again, carbon stays the same, still 4 bonds, 4 electrons. Nitrogen now has 1, 2, 3, 4, 5, 6 electrons compared to 5 valence, gives us -1 for the nitrogen. And my oxygen, 1, 2, 3, 4, 5, 6 electrons credited to oxygen. It has 6 valence. Its charge is 0. This is better because now we've minimized the formal charge on individual atoms. We've had small formal charges on the individual atoms, but the negative charge isn't on the most electronegative guy. So the best Lewis structure is OCN here because now nitrogen, 1, 2, 3, 4, 5 electrons nitrogen with 5 valences. Carbon, again, 4 bonds gives it 4 electrons, no lone pairs. Its formal charge is 0. Oxygen, 1, 2, 3, 4, 5, 6 electrons, plus 1 electron from the bond gives us 7, making oxygen's formal charge negative. So now we have the best Lewis structure because we've used our formal charge to predict the most stable one following these 3 rules. So that's how we use formal charge. If we're not sure between 2 Lewis structures, we can look at the formal charges, and that's going to tell us what the best Lewis structure is. Now, time for some fun. So we had talked about NO3 minus and NO2 minus, right? Who knows what nitrogen compounds are used for? Most commonly. Fertilizer. What's the more fun use for nitrogen compounds? Blowing things up or setting things on fire. So that's what we're going to do here. We have 4 gunpowders, and we are going to have the gunpowder race. So, as they're coming into the starting blocks, we've got UNIC on the inside post, Bullseye and R22 in the center, and SR4759 on the outside. Coming down to the gates now. We're getting ready. And they're off. Oh, UNIC and Bullseye stumble out of the gates. It's a heat between R22 and SR4751 as they come down the back curve. I've got R22 in front by a length. UNIC and Bullseye behind because of the bungled start. And we're making SR4759 on the rail, making a run on the rail. It's got 2 lengths as we hit the back stretch. And we're coming down the back stretch. SR475 in front by a ton. UNIC, Bullseye, and R22 now fighting for second. Bullseye makes a push up the middle. SR475 in front by 8 lengths as we're coming down the back stretch. SR4759 on the back stretch, 10 lengths. Bullseye pulling out in front, 4, pulling into second place, but I've got SR4759 by a mile, getting up to 10 lengths as we hit the back curve. SR479 coming off the back curve, Bullseye making a late charge. I don't know if it can make up the 12 lengths on the back stretch. We've got SR4759 closing, slowing down as it comes on the front stretch. UNIC and Bullseye going for third. R22 making a push there, and it's Bullseye overtakes SR4759. Bullseye coming down the front stretch. Bullseye takes the lead there, neck and neck. I got a length as we're coming down. Bullseye by a length. SR4759 fighting for second. R22 in third. UNIC bringing up the rear. They're coming towards the finish line. It's Bullseye by 2 lengths. Bullseye with the charge down the back stretch wins. SR4759 takes second place. They're fighting for third now. UNIC is closing down R22. What a poor showing. UNIC overcoming the late start, coming in to finish third place. R22 in fourth. And it's SR4759 with the win. Bullseye in second. R22 on the way to fourth place. What a poor showing from a good horse. That's the gunpowder race. Have a good weekend.